In this lecture, we're going to talk about carbocation stability. Previously, we talked about how electronegative atoms can destabilize positive charge. For example, if you were looking at this slide that we talked about a couple of lectures back, we have a positive charge in the oxygen and it's being destabilized by an electronegative atom. Now in this lecture, we're going to talk about carbocations. Carbocations have a positive charge on a carbon. On the left here you can see methyl cation. We have a primary carbocation. Remember that a primary carbon is attached to one other carbon, so that means this R group over here is a carbon. And then we have a secondary carbocation over here and a tertiary carbocation over here. Let's draw some specific examples. This is an example of a primary carbocation. So we have a primary carbocation, and now I drew a secondary carbocation. And this is a tertiary carbocation. And what you can see here is that tertiary carbocations are much more stable than secondary carbocations, which are more stable than primary, which are more stable than methyl. So the trend that you want to remember here is tertiary is more stable than secondary, is more stable than primary. And you won't see methyl very often, but it's good to remember that those are the least stable type of carbocations. Now, why does this happen? Why are tertiary carbocations so much more stable? This is due to an effect called hyperconjugation, and hyperconjugation helps to stabilize these cations. Here's a picture of hyperconjugation. Hyperconjugation is nearby carbon and hydrogen bonds donating their electrons to stabilize a positive charge. Let's draw out this example here. And so in this example, you can see the electrons from the nearby carbon-hydrogen bond donating in and stabilizing the positive charge. And that's what this picture over here is trying to show you. A carbocation is sp2 hybridized, so that means it has an empty p orbital, which is this purple thing over here, and the empty p orbital can accept electrons nearby. Methyl cation, and it's shown over here, does not have any nearby carbon-hydrogen bonds that can donate in. Now let's look at a tertiary carbocation. And you can see here that we have lots of nearby carbon-hydrogen bonds with electrons that can help to stabilize this carbocation. So the more nearby carbo-hydrogen bonds you have, the more stable the cation is going to be. And you're going to have more nearby carbon-hydrogen bonds with tertiary carbocations. Remember, our trend here is tertiary is more stable than secondary, because tertiary carbocations will have more carbon-hydrogen bonds. Then we have secondary, and then we have primary, which is only going to have one nearby carbon-hydrogen bond. Here's a reaction coordinate diagram, and this actually isn't a reaction we've covered before, but it's showing a double bond, and a double bond can react to form either a positive charge on the left or a positive charge on the right. And it's showing the two possibilities. A tertiary carbocation in this case is going to be more stable, right? It's associated with this lower energy here. It is also faster because the hump is lower. Remember that hump corresponds to a transition state. The primary carbocation is less stable and forms slower. The less stable carbocation has higher energy than the more stable tertiary carbocation, and it is also formed slower because the energy needed to form it is much greater than the tertiary carbocation. That's all I have to say about carbocation stability for now, and we're definitely going to do way more on this later.